So in this fourth lesson, we're going to take a look at some polynomial theorems. And we're going to start with a very important one called the fundamental theorem of algebra. And it says if you have p of x as a polynomial of degree n greater than 1, then p of x, meaning polynomial function, that's why they use a p, has exactly n roots, including multiplicity and its complex roots. So let's kind of decode that. What is that talking about? Well, the most basic polynomial is a horizontal line y equals 2. It's a constant monomial. It has no roots. Why? It has a degree of 0. That's why this theorem says it has to be greater than or equal to 1. But as soon as I put an x here, this has a degree of 1, and that means that it's going to cross the x-axis at exactly one place, and this right here is the root or the 0. Now, if I change this to a square, right, if I change this to a square, then I have a quadratic, and that quadratic would look like this. And yes, this one only touches it once, but as we know, we could put a minus, I don't know, minus 2 here, and then all of a sudden it's below the x-axis and it's touching it now 2 times. And so it says you have exactly n roots if you include multiplicity. Well, the original problem I had there had a multiplicity of 2 at the origin because it was a double root at the origin. And the complex roots would show up more likely, they could show up with a quadratic because you know it can't cross the x-axis, but I'll give you a very good example of one from a previous unit in Unit 2. If you had y equals x to the 3rd power, okay, and you said plus 2, well, that would graph, remember you would move your vertex up to 2, you would draw your cube, and according to the fundamental theorem of algebra, there should be 3 answers. I only see 1, and the reason I only see 1 is there's actually 2 complex answers. And so notice what it says, it will equal this number if you include complex roots and real roots and any double or triple roots. So a way to sum this up is the sum of all the roots that you could possibly have equals the degree of the polynomial. That's what it is in just kind of layman's terms. So we have a corollary to that that says when using the fundamental theorem of algebra, all the complex roots have to come in pairs. Like, how did I know there were 2? Why isn't there just 1? And the reason is you get a complex answer by taking the square root of a negative. But when you take the square root, there's a plus or minus, which means when solving, it's always plus or minus some I. So if somebody gives you a problem and says, hey, there's a root of x equals 3i, please find the rest of the roots, you get negative 3i for free if you know this corollary. So that's really good. If there's only 3 possible roots, I just found 2 of them. All right, so if I take a look at the next theorem, I actually combined, traditionally, these are actually 2 separate ones. I put them together. And basically what it is it's a theorem about roots and factors within polynomials. So for any real number r is a root of a polynomial of f of x if and only if the following 4 things are true. So the first thing is r is a solution to the equation f of x equals 0. And that's basically just the definition. If I call something a root or a 0, that means that the polynomial will be solved to become 0 at that value. Basically, it means that I factored it, I set them equal to 0, and I found it to be an answer. Okay? So let's say that answer is r. Well, then if r is an x-intercept, I would then write it as r comma 0 in a parentheses to indicate that it's an x-intercept, as we've learned in previous chapters. Well, that r could then be written as a factor because it had to come from a factor, and that factor would be x minus r. Please keep in mind you change the sign of r from root to factor or factor to root. So whatever this is, this will be the opposite. Let me give you an example of that. So let's say we had, as an example, let's say one of my zeros was x equals 2. Well, my x-intercept would be 2 comma 0, and the factor that produced both of these is actually x minus 2, okay? And of course, if I used a negative number, right, so let's just go back and rewind this for a minute, and let's say I started with x equals negative 4, well, then my x-intercept would still be negative 4, it's just another way of writing the answer, but the factor that produced it would be x plus 4. All right, and then these are all things we've been learning since quadratic, so this shouldn't be a big deal. It also applies to other polynomials because keep in mind a quadratic is a type of polynomial. But then here, the last one is very specific to the polynomial chapter, and it says if f of x is divided by x minus r, meaning if I divide by this factor, if I use long division, or if I use x equals -4 for synthetic division, the remainder is always equal to 0. Meaning, if I do long division with x plus 4, my earlier example, and I do long division, then I do all this work, blah, 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 and I get 0 at the bottom. Or if I did synthetic division, and I used x equals -4 out here, of course, we would just put a -4 there. So if I put a -4 out there, I would do all this work, blah, 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 and I would get a 0 here. Now that's a pretty powerful thing to know that you'd get a 0 here and a 0 here, either if you use the factor or the root. Why is that so important? Because this allows me to factor. And the conclusion is that the divisor, the thing I divided by, as well as the quotient, the thing that would be up here, or with synthetic division, the thing that would be down here, they are factors of the original problem. So the conclusion here is, which is really interesting, is that factoring is the universal way to factor any polynomial, including a quadratic, which is very interesting. A corollary to that is the remainder is always equivalent to direct substitution, right? So if this is true, then this would mean that if I put in r, I would get 0. But it's also true if it doesn't come out to 0. So like, let's say somebody asked you to find f of 3, right? And you put a 3 here and you did synthetic division, then whatever this number is, that's what f of 3 is. Blah, 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 blah. You get 11, then f of 3 is actually equal to 11. So that's a lot of talking. Why don't we look at some examples? Most students understand this better when you see concrete examples. So that's what we'll do next. All right, well, why don't we start with an example where we just left off with that corollary. So basically what this is saying, okay, so using the factor and root theorem, for example 1, use synthetic division to evaluate a function at the given value of x. Well, we learned, back in Unit 1 or even in Algebra 1, that if I want to find f of 1, this simply means that we plug 1 into the equation where we see x's. And so I did 1 because it was simple. Once you see this process and you see the power of this process, you'll understand why it's very valuable on something like an AP test where you're not given a calculator sometimes to evaluate things. So this example here is perfectly easy to just do the normal way. 1 to the third power would be 1, so 1 times 4 would be 4. 1 squared is 1, so this would be -3. 5 times 1 would be 5, and then the -2 constant stays there. So then we would just combine like terms, and we'd get 4 minus 3, which would be 1. 1 plus 5 would be 6, and 6 minus 2 would be 4. So f of 1 evidently is equal to 4. So using polynomials, using the factor root theorem, I know that this means that x is equal to 1. That's what this is saying. That is what we did in this other problem. We put x equals 1 in. So I'm going to put that outside of a synthetic division box. I'm going to put my coefficients right here, as we've learned. And then I'm going to do synthetic division. 4 plus nothing is 4. 1 times 4 is 4. -3 plus 4 is 1. 1 times 1 is 1. 5 plus 1 is 6. 6 times 1 is 6. -2 plus 6 is 4. So the remainder theorem says, hey, that number, actually it's the corollary to the remainder theorem, says that this number is exactly the same as this number. So the result is that f of 1, remember we got 1 from here, will produce an output value of 4. Now you might say, big whoop to doodahs, you just plugged in 1. This would work even if it was -37. It would still work. And -37 would be basically crazy to put here, but here it would not be so bad. So that's the benefit of knowing that corollary. So what else does the factor and root theorem do for us? Well, in problem number 2 here, we have a problem that doesn't factor. And so actually it might factor. It is a quadratic. In fact, it would. And so this first example, I'm going to show you that you can actually use the factor and root theorem to factor a quadratic that previously we may have had to use the box method or or grouping method. So here's how it works, same way. We're going to take 4, right? It says x equals 4 right here. We're going to put it on the outside of the synthetic division box. We're going to put a 2 here, a minus 11, and a 12. Just remember that, this is where the square goes, this is where the x goes, and this is where the constant goes. And if this is a 0, remember the factor and root theorem says if this is a 0, then I have factored the problem and the answer will be in the division. So let's take a look at what this looks like. 2 plus nothing is 2. 4 times 2 is 8. Negative 11 plus 8 is negative 3. 4 times negative 3 is negative 12. And so here I get 0, which means that this problem has been factored. As opposed to the original problem that we did where it came out to 4, right? This just means this is the answer. This would be the answer, but basically the connection here is if this is a 0, it had to have come from a factor, right? This is saying this is a 0. And so what factor did it come from? Well, it came from x minus r, or x minus 4. And the other factor is right here, because if this is a square, we learned in synthetic division that this will be an x. And if this is an x, this will be a constant, and the constant produces no remainder. So I would simply get my other factor would be 2x minus 3. And you may recall when we did quadratics that those would be the factors of this. In the quadratic world, we used a box, so we'll just do that again to show you that it does work out to the same thing. So we would start with 2x squared as our our first coefficient. Then we have to lock in 12. Okay, so we look at this and we say, okay, well, how did I make 2x squared? I did a 2x and an x. 12 has a lot of factors. I could use 1 times 12. I could use 2 times 6. I could use 3 times 4. Please keep in mind that 12 is unreasonable, and 2 and 6 can't work because if I put a 2 here, I have a GCF. And if I put a 6 here, I also have a GCF. So the only thing that makes any sense would be to use 3 and 4. Again, I can't put a 4 here because 2 and 4 have a GCF. So I would instead use 3 and 4. I would multiply it through. I would get 8x. Here I would get 3x. And then I would have to come back to the problem and say this problem is an addition problem. This problem is an addition problem that is going to yield negative. So they both need to be negative, because a negative times a negative is a positive, so they would both be pulled out to here. And then you can see I got the same factors as I did by using synthetic division. So the question is, where did I get this from? And that will be the next theorem we learn. Like, where did I pull that number from? We will learn that in the next theorem. All right, so staying on this idea of what is the purpose of the factor and root theorem, let's take a look at how to factor this problem here using division as well. Now, you may say, how come you're not talking about the fundamental theorem of algebra? Because we're not currently solving. Right now, we're just factoring. Remember, solving will come later when we set things equal to 0 and try to find their roots. Right now, I'm just giving you some roots. By the way, that's a root. So what do I do with it? Well, you wouldn't try to factor this way. You would probably try to factor this since there are 4 terms. We learned in our last lessons that we would try to use grouping, right? But it doesn't group. You can take out a 2 here, and here you can take out an x squared, but I'm not going to get the same thing in these parentheses. So we're going to move to the factor by division way. But again, where in the world did I get this number from? We will explore that in the next and last theorem for polynomials. So we're just going to assume, okay, thanks for the 2. So I'm going to put a 2 here. And then I'm going to do my inverted synthetic division box, put a 1 here, a -7, a 14, and a -8. Please be aware if anything were missing, like if there were no x squared, I would still put a 0 there, just like we learned earlier. But here, that's why I like to label this up here. It's a very good habit to be in, because if you label this going in descending order, then you always catch to see if you're missing something. So 1 plus nothing is 1, 2 times 1 is 2, -7 plus 2 is -5, 2 times -5 is -10, 14 minus 10 is 4, 2 times 4 is 8, and lo and behold, we get a 0. We kind of knew that because it told us we could use it here. And so this right here, the purpose of this is to tell you that you have a 0, right? That's what that actually means. And so what that means is that this will yield the factor of x minus 2, And then this is a square, so this will be, this is a cube, so this will be a square. This is a square, so it'll be an x. This is an x, so this will be a constant. So that'll yield this quadratic. And this is why the quadratic chapter is just so incredibly important. So now we're just going to factor this using the same methods we learned. Now, you might say, why do I have to factor it again? Because you have to keep factoring no matter what. And one of the things that the root and factor theorem says is that there are 3 zeros, and that means there are likely 3 factors. Currently, I have 2. So to factor this, I just start right here. I go forward, right? Notice there's no coefficient, so I can use the easy factoring technique. I have 1 times 4, and I have 2 times 2. And I need to add these together to get 5, so clearly it's 1 and 4. And so I'm going to have x minus 2. And then for this one, I'm going to put my 2 factors here. I'm going to put my 1 here and my 4 here. I'm going to put my x's here. And then to get a negative 5, I need 2 negatives to make a positive 4. And this produces the 3 factors that we're likely to get from having a cube. Again, this number means that this is likely. It doesn't mean it's possible. Remember, the fundamental theorem of algebra says there's this many or less if you include imaginaries, and imaginaries can't be factored. All right, so we're going to look at one more theorem and then repeat this process once we figure out how we got this thing. And that's the next theorem we're going to talk about. So now we're going to talk about the rational root theorem. Such an important theorem because it tells us where we get that mystery number that provides the factorization. So this is a standard way that textbooks will denote a polynomial. Keep in mind, this looks a little intimidating, but what it's really saying is, like, if you start with an x to the 5th power, the next one would simply be like an x to the 4th, and then you'd have an x to the 3rd. That's what it means. You just count down, like we've done in synthetic division, and you're going to count all the way down until you get to the linear term, and the next thing will be a constant. Okay? So understand that part of it. So n is a whole number degree for polynomials. You have to have a whole number degree. So q is what's known as the leading coefficient, and p is what's known as the constant at the end of any polynomial, which, by the way, that constant, when you plug 0 in, will provide you the y-intercept. So I add that little piece in when I talk about this. So the mystery number that we saw previously comes, and this is what the rational root theorem says, if I have a polynomial, then all possible real rational roots. So what are real rational numbers? Remember the sets of numbers, right? We have your natural numbers, 1, 2, 3, 4, so on. Then you have your whole numbers, which include 0. Then you have your integers, which include negatives as well, right? And then you have your rational, which basically means fractions, as well as these numbers, right? So in between 1 and 2, you know, you've got a third and a half and all those things. And that's what it means by real rational roots. It is not talking about square roots of 7, right? It's not talking about imaginaries. It's not talking about pi, anything like that. Those are irrational or imaginary, right? This is imaginary. These are irrational. So real rational roots are found using this ratio. You take the constant, you factor it out. You take the coefficient, you factor it out, and you divide them. So if you take the factors of the constant and divide by the factors of the coefficient, and add a plus or minus to that, that will provide you a list of all the possible roots. Now keep in mind that those possible roots are like sending out invitations to a party. They're invitations only. They need to be confirmed by taking them and checking them to see if they have a 0 remainder. So you may have a long list. You may have 10 of these, but you're not going to try the crazy ones. Like, you're not going to try the 1/3 and the 1/2. You're going to try the integers. 1, -1, 2, -2, okay? So in the next 2 examples, we're going to look at how to use this to make a list of maybes, right? The maybes to your party. And then we're going to use synthetic division to find out, well, who's going? The ones that are going are called zeros or roots, right? And that number of things is going to match up with, if you include imaginary and multiplicity, double and triples, that will add up to the degree of the polynomial, which is the fundamental theorem of algebra. But again, this theorem kind of ties everything together. It gives you the loose end. It ties that loose end up of where did I get this number right here? Well, you can kind of see it right now. Like the 12 if you write out all the factors, it's a factor of 12, and you divide it by a factor of this, so 4 divided by 1 is 4. And down here, like, where did I get the 2 from? Well, it's a factor of 8. So not all of them will work, because obviously you had other kinds of factors there. So like when I look at this one, I've got factors of 10 and factors of 2, and we're going to look at that example next to figure out what the list is, and then who is a 0. All right, so here's the first example, and you can see I've highlighted. So you don't ever have to write this factors of p over factors of q down. I just wanted you to see the traditional way it's written. To make a list of the possible roots, you need to make a list of the lead and constant. So the possible factors of 10 are 1 times 10 and 2 times 5. And then what we're going to do, and again, if you just want to remember it as plus and minus the factors of the constant divided by the factors of the lead coefficient, then we're simply going to put them in order here. 1, 2, 5, and 10. And on the bottom, we're going to put the factors of the lead coefficient, which are 1 times 2, in order, 1 and 2. And then we're going to write out all possible ratios that this can form. And the easiest way to do this, the absolute easiest way to do it, is just start here and take 1 and divide it by these two numbers, or then this and divide by these two numbers. Just one at a time, very methodically. So this is going to come out to plus or minus 1 divided by 1, plus or minus 1 divided by 2, plus or minus, and then start to the next one, 2 divided by 1, and then plus or minus 2 divided by 2, and then plus or minus the next one, which is 5 divided by 1, and then plus or minus 5 divided by 2, and then plus or minus 10 divided by 1, and then 10 divided by 2. So I'm going to tell you a very important thing to understand about this theorem. And we learned this all the way back at the very first thing we taught. You don't include repetitive values. Repetitive values means any fraction that is going to reduce other than ones that have a 1 on the bottom. They're going to be always repetitive. For instance, 2 over 2, don't need it because it's the same as 1 over 1. And 10 over 2, I don't need because it's really 5 over 1. So just keep that in mind. That's very important. So as you're writing them down, if you write down a reducible fraction, you don't actually need to write it down because it's going to reduce to a previous choice. So the possible roots that may be roots of this function in order, it's important to put them in order, would be plus or minus 1/2, plus or minus the next one, which would be 5/2. No, that's not right. Plus or minus 1, forgive me there. And then plus or minus 2, then plus or minus 5/2, and then plus or minus, so I like to cross them out if you get confused. So we've used this one, or put a check mark, I use that one, I use that one, I've used this one, I've used this one, so I need to put 5 in there, and plus or minus 10. It's a very good habit to kind of check them off so you don't leave them out. And technically this is a list, and we learned at the beginning of the year that lists need to have a curly bracket around them, technically. So now we need to find the actual roots using synthetic division. Since all these are singular roots that are not quadratic, we can use synthetic. When I said singular, another term for that is linear roots. So here's the thing. We don't know which one it is. It's one of these is going to get us started. And so we really only need one since this is a cube, because once I take out one of the factors, the answer is going to be a quadratic. So here's the idea. We go back to the very important theorem that said that if you divide using a root, then that root is a root if you get a remainder of 0, and both the quotient and the divisor are factors of the original polynomial. So let's pick something that's reasonable. I mean, I'm not going to start with 1/2. I'm going to start with 1. And then I'm going to use synthetic division. Okay. The original problem has a cube term, a squared term, an x, and a constant. So let's go get those coefficients. They're 2, -7, 1, and 10. I got those from right here, 2, -7, 1, and 10. And let's see if we get a 0. If we don't, we need to move on. And we'll eventually find one. Luckily, synthetic division is fairly quick. 2 plus nothing is 2. 1 times 2 is 2. So 1 times 2 is 2. -7 plus 2 is -5. 1 times negative 5 is negative 5. 1 plus negative 5 is negative 4. And 1 plus negative 4, 1 times negative 4 is negative 4. And then when I add this, I don't get a 0, I get 6. So this means, in this particular problem, I know we've looked at synthetic division a lot in this chapter, but in this particular instance, what it means is it means that it's not a root. So I need to keep going and find one that is. Now, don't get panicked. Don't just start going down the list aimlessly. Be methodical. I now need to try negative 1, right? Because it says plus or minus 1. So let's see what happens when we use the same numbers from the original problem, the 2, negative 7, 1, and 10. Let's see what happens here. 2 plus nothing is 2. Then we get negative 2, negative 1 times 2. Then we get negative 9. Here we get negative 1 and negative 9, which is 9. And then 1 plus 9 is 10. And then negative 1 times 10 is negative 10. So look, boom, I got a 0. So on an assessment, students, I'm never going to give you things that are out of the ordinary or take a long time, because I got to keep in mind what I'm trying to assess is, can you use the theorem? So on an assessment, the first 0 to kind of crack the nut open is going to be plus or minus 1, 2, or 3. All right, I'm not going to make it a fraction or be crazy. A fraction may work because of the next step we're going to do, because these are the possible roots. We just found this one. This one says that x equals negative 1 is a root. So now what we're going to do, and that's going to go in our list eventually, is we're now going to write this. Remember, this was a cube factor, a cube coefficient. This was a squared coefficient, This one is an x, and this one is a constant. Got one step ahead of myself there. All right, so that means that this thing will be a square, an x, a constant, and the remainder. So this function that we have here is 2x squared minus 9x plus 10. So this quadratic is currently a factor of this cubic, along with this, right? Because this is also a factor, as we learned previously. This is x plus 1, and here is my other factor. So the question now is if I want to do a complete factorization, this factorization is not complete. So what I'm going to do is I'm now going to factor this, right, using the box method. All right, so this quadratic right here, 2x squared minus 9x plus 10, we need to lock in the fact that this is 2x squared. So working back outwards, one of these has to be 2x, one of these has to be x. It doesn't really matter which one you choose. This has to be 10. So the factors of 10 are, again, 1 times 10 or 2 times 5. I'm going to try 2 and 5. Remember the rule about factoring. You cannot put a 2 here because you've created a GCF. So we really, only thing we can do is put a 5 here and a 2 there. That'll give us 4x. This will give us 5x. Okay, so I'm already seeing the 9 form that we need. Remember, with addition, that means you have to use the same sign. So these can either be both positive or they could be both negative to make a positive 10. So if they're both negative, now we have our negative 9, right? And we need to flesh that out by putting that here, and that negative 5 and negative 2 make positive 10. So it looks like we've created the factorization here for this quadratic, which is 2x minus 5 and x minus 2. Please notice that those would produce roots that were in our original list. Look, this one's going to produce 5 halves. This one would have produced 2. And students will always ask me, does it matter the order? Because what if I like 2 because it's my favorite number? What will happen is you'll get 2 to be a root through synthetic division, and you'll have a different quadratic to factor, but it would contain the other factors of the polynomial that you haven't used yet. It's a magical puzzle that no matter how you solve it, you'll get the right answer as long as you start by finding a root. So to clean it all up, the complete factorization of f of x is going to be, f of x is going to be completely factored, and I like to put them in order of the actual roots. So remember, this one would produce a root if we were to solve it. We already know what it is in the list, but just to show you how I got that 5 halves, here it is. I would add 5 and divide by 2. And over here, I would subtract this and set it equal to 0, so that would give me x equals 2. So please put these zeros or roots in order, as we've learned from the beginning of the year. So in order, my first root that I found right here is negative 1. Then I have 2 and then 5 halves. So negative 1, 2, and 5 halves. And then after you've written down the actual zeros, please write down their corresponding roots also in order. Please order the factors in the order in which the roots produce those factors. And this kind of, again, oops, I wrote that down wrong. Give me 1 second. So x minus 2 here, and then, of course, 2x minus 5. Just make sure you check that. It is an easy thing to do, and it goes back to the problem I did earlier in this lesson that says that this is always the coefficient, and this is always what you add or subtract. So the last thing to tie everything together, is to sketch this graph. So when we sketch the graph, we're going to, put an axis on here. Polynomials, the chapter in general, is just trying to make you make a lot of connections about factoring and about zeros before we move to other things in Algebra 2. So the zeros are 2, and then we also have one at negative 1, and then 5 halves. Oops, I somehow graphed that wrong. Let me try it one more time. 2 is here, and then negative 1, and then 5 halves is 2.5 right there. None of them are double roots, okay? We know that the end behavior of this graph is positive. So remember my hint about putting that on the graph. The right side is going up. And we know that it's a cube. So being that it's a cube, we need to have 2 turns on the graph, right? So and we need to have it end up going up. So here we go, going up. There's the first turn. There's the second one, a little hump right there, and then going up. All right, so you might want to watch that again and just kind of understand and comprehend all the different steps. It is really interesting how it all connects together, especially if you're a mathematically minded person. It is kind of, in a way, a beautiful puzzle. And you might want to actually try. It would be a great thing for you to do, to complete the problem on your own. But instead of using 1 and negative 1, start with 2. You will end up with the exact same answer as me. You'll just get 2 first, and you'll get the factorization of these in your quadratic step here. So in our second example of the rational root theorem, I provided a slightly higher degree problem, and this will cause some interesting things to happen, though the process will not change. So let's begin with what the rational root theorem says. It says if I make a possible list using the factors of the constant divided by the factors of the lead coefficient, that I will produce a list that will provide zeros so I can factor the polynomial. So 16 has 3 factorizations. 1 times 16, 4 times 4, and 2 times 8. So I'm just going to put them in order to help us organize it in a minute. Try not to do that just randomly, right? You want to try to put it in order from the beginning. So those numbers right there, what we are going to do is we're going to put them in our list in order. And when we do that, we're then going to put the numbers below it in the list as well. Notice that the 4 occurs twice, and we learned in the very first lesson of the year that we do not write things down if they're repetitive in algebra. So it looks like we have that list now. And now if we look at the coefficients the coefficients factors, we only have 1 and 3, so it's not a lot to do there. And now we are going to take those numbers and we are going to make a list. Again, we're basically going to take this and divide it by 1. So last time I did 1 divided by these 2, and this divided by these 2, and this divided by these 2. If that was tedious, maybe try this. Take each one of these numbers and divide them all by 1. Maybe that will be more effective for you. Please make sure you include a plus or minus on each one of them. I know it is tedious, but if you do not, technically your answer is only half as long as it needs to be, and that can be very frustrating to understand how to do the theorem, but then only get half the answer right. So I took each of these and divided them all by 1, and now I'm going to take each of these and divide them all by 3. So 1 divided by 3, and so on. And in this problem, none of these right, so far have reduced. In fact, none of them do reduce. So the interesting thing about this problem is we don't have any reducing fractions. So everything that is produced by this list is a possible root. So now we need to put that list in order. The smallest thing that I see is a third, and then 2/3, and then 1, because 1 divided by 1 is 1, and then 4/3, and then 2, and then 8/3, and then 4, and then 16/3, and then 8, and then 16. Sometimes one way to make sure you have them on the list is simply count. So notice here I have 10 things. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That way I just know I didn't leave one out. So there is a mess of things in here. Only 4 of them, right, because of the fundamental theorem of algebra, only 4 of them can work. So I'm not going to start with any crazy ones. I'm going to start with 1. So I'm going to start with 1. And when I use 1, I'm going to take the coefficients of the original problem, which would be, again, we have a quartic term, cubic term, quadratic term, a linear term, and a constant term. And here are the coefficients: 3, -13, -8, 52, and -16. And all we're trying to determine right now is, do we have a 0 at the end? So 3 plus nothing is 3. 1 times 3 is 3. Add these two together, you get -10. -10 times 1 is -10. Here I have -18. 1 times -18 is 18. I can already stop. There's no way this is going to cancel out. So you don't even have to complete it, because we're not doing division. We're checking to see if the division is going to produce a root, produce a 0. And if it doesn't, there's no reason to continue. This is not part of the answer, so I can stop. Let's take a look at -1. So 3 plus nothing is 3. Times this would be -3, and then -16, 16. Here we would have 8. Then -8, there's no way that's canceling out 16. We will now move on to 2. So see if 2 works. And again, sometimes you have to go through a couple, but as I told you, on an assessment, it's either going to be plus or minus 1, plus or minus 2, or plus or minus 3. That way you know you'll get there eventually. And if you don't find one, you'll know to go back and check your work. 3 plus nothing is 3. Here we have 6. Then we add this together and we get -7. Multiply this, you get -14. Here you get -22. Here you get -44. It looks like we're going to get it, because here you get 8. And 2 times 8 is 16, so we got a root. And remember, if this is a 4, 3, 2, x constant, this will be a 3, 2, x constant remainder. That right there says this is a root. Okay, so now what we're going to do is see if this will factor. So this thing is 3x cubed minus 7x squared minus 22x plus 8. And in a great ideal world, this would factor by grouping. This one clearly doesn't. There's no way to take a 3 out of a 7. So believe it or not, you can actually just keep going with synthetic division, not using the ones you've already done. These are already done. So check, check, check. I don't want to use them again. I can now start with -2 and see if it will work. It doesn't, so I'll show that to you. So we can start again with the division process, with not with the original function, but with this factor. Remember, this is a factor, so we want to factor it more. So here we get 3, -6, -13. This times this would be 26. Hold on, it does work. Forgive me. So don't discount the very next one, right? Here we get 4. Here we get -8. So sure enough, It did work. So don't discount the next one. Check it, right? Because right there, if I would have moved on to 3 might have worked. Don't worry, the order is not important. What's important is to find the root. So this is also a root. That's good news. Okay, so now what we're going to do is we now have found 2 roots. Okay, and so now we have this quadratic, because it was a cube, it's right there. This is now a quadratic factorization, and that is good news. That's how you know when to stop, right? Because when you have a quadratic, quadratics either factor, or you can find their roots with the quadratic formula. This one will factor. Let's take a look. I can already see that it will. So what happens is we're going to go ahead and start with the fact that we locked in 3x squared, which was locked in with 3x and x. And then we have 4, which is going to be locked in with 1 times 4 or 2 times 2. So probably 1 and 4. And the reason I say that is this is 13, and if I put a 4 here, I'm not 12. So I bet it's going to work with 1 and 4. So, oops, those go on the outside. So if I put a 4 here and a 1 here, right, we would have x and 12x, and now we need to add these together. We do have 13, just like the other problem. When you have a positive number, these factors can both be positive, which they're currently written as, or they could be -1 and -4. So we're going to make them both negative, which would then make these numbers negative. It would keep this positive. That doesn't change. So now we found the rest of the factorization right here. It would be 3x minus 1 times x minus 4. So now let's put everything together. Don't forget, this is also a factor, x plus 2. And this is also a factor, x minus 2. So if we put it all together, what are the actual zeros? In order, right? The zeros are, and again, they're in the list, and I'll show you that in a minute. So the smallest one we have is -2 right here. The next one that we have is this one, which produces a third. And then after that, we have 2 and 4. So if you're wondering how I got those, all I did was I set these equal to 0 and solved them. So the complete factorization of this, following the pattern of the root so that we all agree on the order, would be x plus 2. This one would be 3x minus 1. Remember the rule of this is the coefficient, and this is the number that goes here. And then x minus 2, and then x minus 4. And please notice that huge list that we had originally contained a third plus and minus 2, and the other one, which was 4. So now we're going to sketch a graph. We have recopied that down here. So why don't we just get a little bit better at it in terms of how could we do a good job with this with some information that we've learned in this chapter. So the first thing is, let's just start by graphing our zeros, right? So if I graph my zeros, I would have one at -2. Not quite big enough. Let me try again. So -2 and 2 and a third and 4. We can easily find the y-intercept as well by plugging 0 in. And we don't have to plug it into this complicated one. We just plug it in here. Remember, the y-intercept is simply this number right here. So we plugged in 0, and we're going to get the constant every time. So maybe what we'll do on this graph is we'll show that we're going by 1s here, right? But on the y-axis, maybe we go by 4s because we have to go to -16. Or, so 4, 8. And you're allowed to do that. The x and y-axis can have different numbers on them as long as you're consistent on that axis. Okay, so I'll do that up here a little bit too. And so now I can graph that intercept. I'll change the color on it so that we can see that it's different. I'll make it blue. And so then after we graph that y-intercept, what we'll do is we will then think about the sine of the coefficient. That is positive. So that means that it's going to go up here. So we'll have to graph it so it does that. And being a 4th degree polynomial, it will have 3 terms. Remember, the relationship is this -1 tells you the terms, but if I'm looking at the graph, that will then be to add 1. So you have to make sure you understand the perspective. None of these are double roots, so everything's going to look nice and linear, and it's going to have this with an even degree, that means we start going up here. So remember, right tells you what to do based on the lead coefficient, and left is decided by the fact that it's an even degree. So let's take a look. I think it's going to look like this. So we go down here. We have 1 turn, 2 turns, 3 turns, back up to that arrow that I already drew. So there's a lot of prior knowledge to make this graph, but it really does help link everything together. So hopefully this last section is helping the whole chapter make more sense, or just maybe become more concrete. Hope you enjoyed this video and this lesson.